posting a visiting candidate for the analytical chemistry position. If you're in inorganic, you're going to get to see them lecture in class on Friday. If you are in, is it surveyed at least Thursdays? You're going to get to hear your research presentation tomorrow. And that overlaps with my office hours, so I got to change some things around. So my office hours are going to be earlier in the day on Thursday. And I'll get those posted up on Blackboard. Again, another reminder, tip night, we need your help. We can't do it by ourselves. And so please come and we'll try to do it. And then chemistry jobs are open.
Are you going to think we're not studying for our exams if we're all there?
I think you're taking a stinking break. Just recharge.
We can have flashcards all over. Just put like practice problems all over the hallway. We can only put decorations here if you answer this correctly.
Well, I won't be much help though.
Yes. Alright, we've had a little bit, and I have to apologize, I have no memory where we stopped. Is it mechanism?
What day is it?
So we broke down the catalytic triad.
21st?
Okay.
20th. That's the 21st.
That helps.
Definitely 20th. Oh. Get behind it.
Okay.
No.
So, picking up right where we left off. Alright, so you form terms of tetrahedral intermediate. And it's something that's not very easy to track. Well, they have evidence for it, so you can call this carbon transition state. Because it is variable. It decomposes and peptide bond is broken. This is mediated by histidine 57, which protonates the amine as it leaves. Oh, sorry, the terminus. So what type of catalysis is that?
Acid base?
Acid catalysis. So the new N-terminus leaves. And the new C-terminus is still covalently linked to our enzyme. So no water enters the active site. And the seal is hydrolyzed. In a reverse of the acid-base catalysis. Done by the same. So it's just a reverse process of what happened before. And we'll go back on the picture. protein that you're going to hydrolyze, so peptide bond, and this chymotrypsin has to be something next to a hydrophobic amino acid. And you have that catalytic serine that nucleophile attacks, mediated by the base catalysis from the histidine that makes the tetrahedral intermediate. This collapses, the carbonyl collapses back down. When it does, the peptide bond is broken, and then it's mediated by histidine, which donates the proton. Where are we? Okay, so then we're broken. This just leaves. Water comes in, and now water is going to nucleophilically attack the carbonyl here, where we're still attached to our catalytic serine, mediated by the histidine that's going to pull out the proton and make this a better nucleophile. We reform the tetrahedral intermediate, which is going to collapse again, but this time the serine is the leading group, again mediated by a histidine. And then this whole new sequence can leave, and we've regenerated our active site again. So you've got lots of different types of catalysis going on. So in the last two I've asked you, well, how can you improve your mechanism? This one I'm going to just kind of outline what is known about the mechanism. First is labeling. And labeling we hopefully saw in the paper that you just read for today. But the use of amino acid specific labels help identify your catalytic residue, the serine. So TPCK, I don't know this time. So we have TPCK and DP or DIPF. Okay. So TPCK is a histidine specific label. DIPF is a serine specific label. And if you can label your catalytic residues, then you can prevent catalysis. So it's a way of looking to see, are there any histidines in this molecule that are important for catalysis? And labeling them might disrupt that. Are there any serines that are important? Are there any cysteines that are important, which we saw in the paper? So for, again, the chymotrypsin, one of the catalytic triads is that histidine. TPCK is this tosyl-L-phenylalanine chloromethyl ketone. Nobody remembers that. Everyone remembers that. And you basically just attach this to the nitrogen in the histidine ring, and as soon as you do, then this nitrogen can no longer act as a base or an acid. So you've disrupted its ability to do that. For serine, this DIPF, diisopropyl phosphate fluoridate, kind of a similar thing. So a hydroxyl group gets added to that phosphate, the chloride's the leaving group. And so when you've added this, it actually prevents the serine from being a decent nucleophile anymore. And so, again, you can disrupt that catalytic activity. With labels, you always run into the possibility that your label destroyed the native structure of the protein rather than just disable the catalytic activity. So these are not definitive. You have to have more evidence than just the labeling to figure out if that particular residue is involved in catalysis. The crystal structure exhibits an oxyanion hole positioned to stabilize the tetrahedral intermediate. If that were the case, what type of catalysis would that be?
Oxidoreductase.
Get a little TS there. Does that help? So find the example of preferential transition state line.
Literally the only one we did last time.
So when you look at the crystal structure of the active site, so this, again, this is my cartoon version of the whole enzyme, and then here is the peptide bond I'm going to cut. For chymotrypsin, there's my phenyl ring for my hydrophobic amino acid that's next to the peptide bond I'm going to cut. And there's my catalytic serine, my catalytic histidine, there's the aspartic acid, it's helping to position everything, and then I have this little hole right here that's got a couple of NHs from amide backbone groups that are positioned nicely to hydrogen bond to the tetrahedral intermediate for that oxygen. So when you break open this carbonyl to form the tetrahedral intermediate where we have this oxygen with negative charge, then these are positioned just perfectly to form hydrogen bonding interactions. And so it's thought that we may have some transition state binding going on, so we're kind of promoting the opening of that carbonyl. And so it's preferential binding transition state binding. That's the question mark. That's always kind of difficult to show, but it's definitely stabilizing our intermediate. Through hydrogen bonds with backbone atoms. It is possible to trap that intermediate.
Are we saying that the crystal structure has shown these things?
Well, you have a crystal structure, it's static.
Yeah.
You put in, so either you solve it with a substrate down to it, or you model where the substrate would be binding. And you know, initially they just noticed there's a pocket here that if this is the correct mechanism, you would have that stabilizing interaction. Okay, so initially it would just have been that. They had the structure, they saw this pocket, and it supports the idea of this tetrahedral intermediate. Okay, later they actually discovered that they could trap the intermediate to show that it was the case. Okay. So it is possible to trap an intermediate. Using inhibitors. Under acidic conditions. And there are, oops, I didn't put a picture. I thought I had a picture. There are very specific peptide inhibitors for chymotrypsin and trypsin where they mimic a substrate, but after the carbonyl opens, they get stuck and they can't go any further. And it's not because there's anything special about the peptide bond or anything special about, say, like that phenyl ring that's going to sit in the chymotrypsin pocket. It has to do with how tightly the inhibitor actually binds to the enzyme so that it forces the enzyme to be more rigid than it might normally be. And that rigidity actually prevents the catalysis from taking place. So, they do have good evidence that people are going to get businesses. Okay. So then you guys read paper and you loved it, right?
Obviously. All the time, every day.
During 228, you signed for catalytic activities of the inside fluid and study solid phospholipases. Alright, so this one, hydrolase. It's going to turn out to be a serine hydrolase. So again, I mentioned this catalytic triad. You find it in lots of hydrolases, not just proteases. Shows up all over the place in nature.
I legitimately read this one. Yeah, I do it in pencil. Yes.
And I'll pop the paper up there on the screen.
Rachel, when is your biosec test?